All right, this is for section or chapter 5 of Triola's Essentials of Statistics, and we are on edition 5 now. These notes were made to accompany edition 3, but there are not many changes, so we are going to be using those. All right, in section 5.2, the first thing that I want to talk about is the fact that when I write a capital X, I'm going to be talking about a random variable, and when the capital X is given, that means that I'm writing the description of the random variable. And then when I use the lowercase x, and I use a kind of a scripty x, that's giving the values of the random variable x. So let's take a look at some examples here. So what are the values that x can take on for the roll of a single die? Is it discrete or continuous? So we want to realize that discrete or continuous refers back to what we learned in chapter 1. Discrete random variables being those with with holes in between, countable occurrences, continuous being like a number line, no holes, everything is measurable. And countable and measurable being two words that are commonly used to describe the difference between discrete and continuous. So in the rolls of the die, we can get a 1 on the die, we can get a 2 on the die, we can get a 3 on the die, we can get a 4 on the die, we can get a 5, or we could get a 6. Now we must be on the same page in saying that we're going to talk about a cube die, which is a 6-sided die, which is having numbers 1 through 6 listed on it. And these would, of course, be discrete random variables. All right, now moving on to the second example here. What is the values x can take on for the altitude of an airplane that takes off from San Francisco Airport, assuming that it does not crash? Now, the San Francisco Airport is at sea level, so the altitude values could be anything starting at and going up from 0, so greater than or equal to 0 feet, and that would be, of course, feet above sea level. And this would be a continuous random variable because you could be 0.1 feet above sea level, 0.01 above sea so 100 feet, so on and so forth. All right, now next one we have, suppose a coin is tossed twice so that the sample space S is as follows: heads, 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 tails, 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 heads. Let X represent the number of heads that come up. What are the possible values of this random variable? Well, the number of heads, well, in this case there would be 0 heads. In this one or this one there would be 1, and in this one there would be 2. So there would be 0 or 1 or 2 possible. Again, those are discrete values. All right, now moving on to the next idea, which is a probability distribution function. Now, what you must realize is that we've already encountered these, but they were called something else. We were calling them frequency tables. Yes, a probability distribution function is nothing more than a relative frequency table. The relative frequencies became our probabilities, just like from chapter 4, we were talking about relative frequency probability. And that relative frequency probability is indeed our probabilities that we see here, and the x's, that's the same thing as our classes in a frequency table, or for a discrete one we can just write the 1 through 6's. Now we had an example that I do in for most exercise sets with Triola's book about the ending measures, I believe it is, of heights, and those are the digits 0 through 9, that the measured heights are they're actually reported heights of people could end in. And the way the frequency table is done there is, instead of using classes from 0 to 0.9, from 1 to 1.9, etc., from 9 to 9.9, it uses 0, 1, 2, 3, 4, 5, and that's because they're discrete random variables, and so it very much makes sense. And that becomes your link between a frequency table and a relative frequency table becoming a probability distribution function. So with that little bit of lead-in, let's describe the PDF for the rolls of a single die. So what we want to think about is the classic probability, in this sense, for rolling a single die and the outcomes. So we already had decided that the outcomes for the roll of the die were 1 through 6, and so now we want to associate the probability with that. Well, the probability associated with getting a 1 is there is one possible outcome in the 6 possible. For a 2, 1 in 6 as well. And 3, 1 and 6 as well. 4, 1 and 6, 5, 1 and in 6, and 6, 1 and 6. Now, just as we learned in our relative frequencies, the sum of all relative frequencies, right, should add up to 1. The sum of all probabilities also should add up to 1. Remember back to Chapter 4, the heart and soul of probability. All right, now moving on to our next example here. Our next example says describe the probability distribution associated with the number of heads obtained when you toss a coin twice, this example here. So I've written a little tree diagram out that gave us our sample space that was given in the first set of examples in this section of the chapter. On your first toss of your coin, you could get a heads or a tails, and then from your second toss, you could get a heads or a tails based upon what you got the first time. So this gives us a little tree diagram that helps us to find this sample space down here. Here we have a heads, heads. That's that one right there. And then the next one we would have a heads, tails, and that would give us that one right there. And then next we would have a possibility of a tails, head. That's that right there. And then finally, we'd have a possibility of a tails, tails, and that's right there. So that becomes our sample space. So we already knew that it was possible to have 0 heads, 1 head, or 2 heads when we flipped a coin 2 times. So now, looking at the sample space, we can use again classic probability in order to grab our probabilities here, the P of X's. So if we have 0 heads, that's only going to happen in one way, right? Tails, tails, that's 0 heads. So that's 1 in 4 chance. And then our next one, that one is 1 head. Well, that can happen 2 ways, so 2 in 4, or 1/2 is our probability. And finally, just having 2 heads, that can only happen in one way, again, in a 1 in 4 chance. And what we should be noticing, again, just like a relative frequency, the sum here should be 1. And again, coming back to heart and soul of probability, that this is adding up to 1. Now, we're going to discuss this right here in these next examples. So notice that in the roll of the die experiment, that all of the probabilities sum up to 1, so they did, and that all probabilities are between 0 and 1. Yes, every single one of these is between 0 and 1, meaning it's not over 1 and it's not a negative probability. And again, you're going to look to see that it holds true for the coin example. So we already proved this one. You should also be noticing, therefore, that, yep, that's right. You notice that these are all between 0 and 1 as well. All right, the next thing that we're going to do is we're going to determine whether these following problems here are probability distribution functions. So I'm going to flip over to here. So we have determined, yes, that the roll of the die conforms, and the sum of the probabilities is 1. That was the first thing. And the probabilities themselves, they are all less than or equal to 1 and greater than or equal to 0. And your turn, you confirmed, yes, indeed, the flips of the coin was a probability distribution function because the sum of the probabilities was equal to 1. And then the probabilities themselves were all between 0 and 1. And then these, I think I'm going to just go ahead and say, why don't you pause and try to answer these for yourselves and say whether they're PDFs or not. And then you come back and see if you were correct on that. So, what do you think? Well, looking at these, we have everything in between here, right, being a probability between 0 and 1. So all the probabilities here are indeed between 0 and 1. So that's going to conform. And then I also have to check on the sums. So I say 1/4 plus 1/4 is a half, and a half plus 3/4, well, a half plus 3/4 is 1 and 1/4. Well, that's greater than 1. So that's not going to conform. So no, this is not a PDF because it breaks one of the basic rules that my sums are greater than 1. All right, now the other one, what we're going to look at is the first thing that we see in the probabilities in the second example is a negative probability right here. So even if you look at just nothing more than that, you're going to see that the probability of the x being equal to 0, this one is going to, this one's going to be a bad thing. We cannot have a probability that is a negative value. So this p of x is less than, not equal to, just simply less than 0. And so it is not a probability distribution function. And that's irregardless of whether they would sum to 1 or not. All right, moving on to our next few examples here. So the next thing we're going to do is we're going to draw a probability histogram. So we're going to take our probability distribution functions that we had, and we're going to do for the dice experiment, and we're going to make the histogram from that. This is really no different than the histograms that we were drawing back in chapter 2 or 3. Gosh, I can't even remember now. It seems so like it's been so long ago. So whichever section that was in drawing histograms, we're going to do the exact same thing here. So this is over here, instead of frequencies this time, it's going to be my p of x's equals x's, and you'll have to forgive my sloppy writing because I am having to really write this sideways. And this down here, these are my classes, but these are my random variables. And random variables, by the way, I will most often denote these as RVs. And these are die outcomes. And our probabilities, remember, we're all the same. So this is just, I'm going to represent up here, I'm going to represent that value as 1/6. And I'm not going to put anything else on here. So I'm going to make each of my little bars, I'm going to make them 2 units wide. So there's my first one for the outcome that my die is a 1, and there's the middle for the 2. And you notice that my bars are balancing over the random variables, and there's my outcome for a 3, and my bar balancing for the over the 3, and there's my 4, and again my bar balances over the 4, and then my 5, and my bar balances over the 5, and each of my bars are the same width wide, and we consider whatever that width I have there to be 1 unit wide. And so there's my histogram. Now, I haven't done a great job of it, but what we should notice is that this is right across here even. So just consider it to be even. They're all the same. This type of a histogram shows what we would call pretty much a uniform distribution. Now, you're going to draw the probability histogram for the coin toss example. So let